Okay, so let's discuss what we have found out. We built version 1 of this buck regulator, and it worked, but we weren't happy with the output ripple on the thing. So then I actually purchased some of these cheap Chinese versions of it, and subsequently what I did was I removed all the components to have a look at them, so we can actually I desoldered them. And we found out various things. Number one, we have determined that we can't use ordinary little trim pots like these guys over here. They are not good enough because it is very touchy when you make the adjustments. It's very difficult when you have one of those to actually get the right output voltage. So you need a multi-turn one. That's why they used it here, which we are going to use now as well. Secondly, this chip over here, and they come from China like this. I've got a bunch of them. They are apparently copies of the real LM2596, and also this particular package, the D2 pack or whatever they call it, it has limitations. The only cooling that it gets is from being mounted on the PCB, and this particular thing here, even at 2 amps, it's supposed to be able to supply 3 amps, but at 2 amps it gets uncomfortably hot, and that includes this inductor over here. And furthermore, this diode over here is only rated at barely 3 amps. These capacitors over here have quite a high, they're cheap capacitors, they have quite a high ESR, which according to the data sheet for this particular chip here is not good. And also this chip here appears to be running at 52 to 54 kilohertz, and according to the data sheet, if I read it right, it should be 150 kilohertz. So what we've done is I ordered some better components. Let's move these out of the way. I've got an inductor here which was actually advertised to be just for the LM2596 buck regulators. It is rated up to 6 amps, it says, but the regulator is only rated for 3 amps, so that should be then more than sufficient. I got this proper, let me see if I can arrange it so that it is readable. I've got a proper on semiconductor 2596T adjustable, which is a TO220 with 5 legs on it, so that I've been able to, I haven't tightened it up yet, but it's going to be mounted on this little heatsink, which will help it. And of course I have a proper diode over here, and we are even going to try on the circuit to put an extra filtering on it. So I've got another small toroidal inductor over here, which we're going to mate with another capacitor. Now what I have found out is that, as I said, I bought a bunch of these surface mount capacitors, and none of them, of course, you know, these are Chinese things, none of them have very good ESRs. They range from 418 to 218 milliohms, and according to the data sheet we need 85 milliohms or less. So I have found that I have some ordinary capacitors here. This one says it comes from Japan, and indeed it seems to be the best quality one that I have. And now I salvaged this from some sort of circuit board somewhere, and it has 58 milliohms. So we're definitely going to use this one on the output. Also bought a whole bucket of these ones over here, which were advertised as low ESR. You can see it on there. See, low ESR says so. Unfortunately, this wasn't true. This one has 200, this is 100 microfarad, 264 milliohms, and a 220 has 124 milliohms. So, which is a fairly average ESR for capacitors like that. Now, in a normal circuit, they would be perfectly good enough for filtering and doing all sorts of stuff, but on these buck regulators it is critical that you get the best capacitors you can get your hands on. Okay, so back at the circuit here, what this controller actually does is it measures the output voltage that is being produced via this link over here through that trim pot, which of course we are using to adjust the voltage, and it determines that when the voltage gets too low, it will then switch on and output a positive voltage to the inductor and this diode over here, which then becomes reverse biased, of course. So current is allowed to flow then through the load, and these capacitors over here will actually charge, and magnetic flux, a magnetic field, builds up in the inductor, and then when the controller determines that the voltage is high enough, it will switch off. The inductor then becomes reverse biased, and current will then start flowing through this diode, and in conjunction with the charge that's on the capacitor as well, will then continue to provide currents through the load. And by switching on and off at a particular rate and at a particular width of the pulses, determines how much energy is flowing through the circuit, so it can therefore keep the voltage relatively steady. I think it said in the data sheet that can be up to 4% difference depending on the current, but I think it's a little better than that when you actually measure it, which we'll do later on. So that's part of the circuit here. We are going to add potentially some extra filtering on the output, which is what this inductor and this capacitor does here. It will just present an extra impedance to any pulses that might be coming out of the circuit at this end over here, and filters them out. We have a bypass capacitor here as well, just in case there are some very high frequency short pulses that it will take care of. So that's basically how the circuit works. Now we can have a look at the actual data sheet, and there's some further explanation over there that might clarify it. Okay, so this is the data sheet for the regulator, the LM2596. It's an on-semi data sheet, so that's the very chip that we're using. And it's a little bit better than the Texas Instrument one. It has a little bit more explanation of how it works and so on, and which is what we're looking at. So the actual regulator over here is actually represented by a switch, because really that's what it does. It switches on and off via some powerful output transistors internally to the chip. So let's say that this switch is down, so therefore current is flowing. Now I like current to use real electron current flow that goes from the negative to the positive. So current is flowing over here. The diode is reverse biased, so the current is going to go through the load. It also is charging this capacitor, and it is building up a magnetic field in this inductor. Once the magnetic field has risen enough, then the regulator will decide to actually open the switch, and we kind of see that happening over here. First it's on, stuff is charging, magnetic field is built up, then it turns off. But now, because this is what inductors do, their magnetic field collapses because there's no more current flowing through it, and it will reverse in voltage. So this side of the inductor now becomes negative. So now current starts to flow through this diode because now it is forward biased and continues to run through the load. But this capacitor also will play a role by releasing some of its energy to help level out the actual voltage that is on the load. And of course, this is what we want. We want a steady voltage on the load. Current can go up and down, but we want the voltage to be steady, which is the purpose of the actual buck regulator in the first place. So when that happens, the voltage, of course, will start to drop when the energy out of the capacitor and the inductor starts to be expended. The regulator then recognizes that through its feedback network and switches back on again. And this is what you see over here. So it switches on and off and on and off. It will do so with a wider pulse if it senses that there's a lot of current being drawn in the load. And it will make these pulses much narrower if it senses that there is very little current being drawn in the load. Also, the reason we're using this Schottky diode over here is that, as you can see, when this voltage goes negative on this inductor over here, there is a forward voltage. This is why it's FWD, voltage diode forward, which the diode has, so it won't be conducting until that forward voltage is satisfied. And on a Schottky diode, this is 0.2 volts roughly, but on a normal silicon diode this would be 0.6, 0.7 volts. And this would limit, if this was higher, that would limit the lowest voltage that you can actually regulate with the regulator, and that's why we're using this Schottky diode. And that's also why I think the minimum voltage, what is it now, like near 2 volts or something, that would be limited by that. So therefore, also here, as you can see, there's this triangular waveform which you would see as far as the current is concerned. Current goes up, it goes down, up, down, but we want the current on the load, we want that to be steady according to its load that it is presenting. And this waveform over here, of course, has to be filtered out by the capacitor. Okay, so a couple of things to mention here. In version 1 of the buck regulator, I actually didn't quite explain what you're supposed to do with these traces. I kind of worked it out since then, which goes to board setup. Alright, and then we have net classes, and what you are meant to do is, let me open this up a little bit. Yeah, okay. You are meant to make so-called net classes. I've made one. This is the default one. There's ground, power and VDC I have made up, and they have different sizes for the track width, 3 millimeters, 2 millimeters. You can override that on the actual PCB, which I've done in a few places. I've actually increased it to 4 millimeters, but only where it was possible to do so. And then you go the actual nets. They have names, net C3, pad 1, and so on. You will then assign your ground is assigned to net class ground. These two are assigned to the default. This one here is actually power, so that's going to the power class, and this one is power as well. And then there is the voltage in VDC. This is the proper way to actually do that in KiCad. I just want to mention that because I didn't do that properly on the version 1 when I was showing that. Alright, so what I tend to do is this is a prototype board which we were making up ourselves with Photo-resist, and it's going to be single-sided. So I actually put the traces as though they are on the top side here, because it's the easiest way to work with it. And also, if you have any surface mount components, like originally these capacitors here, that is where they will end up on the top side. Any case, what I do is I do not connect the ground pins anywhere while I'm doing this. I only connect the signal and power pins, and then I will use this filled zone feature over here on the side, and I'll tell it that it is ground, and then I fill the whole board with the ground, and that's what that little outline there is. I make it a little bit proud of the board because it always seems to leave a gap, as you can see it from the cutout there. So then it automatically connects all the grounds together, and you're done. But the one thing that you then have to be aware of is that you leave enough of this ground plane for the ground to actually be connected in a circuit like this where you've got high currents. So this, as you can see, I've made the board a little bit wider than perhaps it needed to be in this case, and left about, I don't know, 4 millimeters or something at the top here, because the whole board, the ground needs to be connected over the whole board, not just in one section. And similar to here where there was a narrowing, I moved components a little bit so that this area leading off to the actual ground pins of the actual regulator here is got enough width here as well, again about 4 millimeters, and similar with the bottom over here. So that is what I do. Now if you develop this board with Gerber files and things, and you're going to actually send it to one of the PCB manufacturers, you wouldn't necessarily need to do this, because you would make a multi-layer board where you can have separate ground planes and power planes and whatever you desire. But at the very least you could make it double-sided and put the ground plane on the back side, and you wouldn't have to worry about that because it would flow through the back. It would have much more surface area there, just as a mention. And you might also notice that I made these traces quite fat in different places, because this is where the main power comes in, this is where the main power comes out, this leads to the diode, and it has to be close to the chip, and it needs to be a large surface area for the low resistance for the traces there. And similarly goes to the inductor, and when it comes out it potentially goes to the second inductor here. So these traces are all made large in order hopefully to make the circuit work. There is an area here which is actually not shown on the PCB here, because I couldn't be bothered to make a separate footprint for it, but that little heatsink needs space, so it goes around, wraps around it like this over here, so that's why there's extra space here for that. So now we are ready to go and make up the negatives. and as usual you would go to the plot icon here, and once you go there you would say front copper, which is what we were developing, and we want a mirrored plot, a negative plot, and also check the zone fills before plotting just in case we've moved something around that needs to be updated. I usually put plot edge cuts on all layers. That little white line that you see over here shows us where the edge of the board is supposed to be, and once we've done that I usually do a second plot and I turn that one off, the front copper, and I'll turn off on the F fab, and sometimes I might do the silk screen, the courtyard, and I will not make them a negative plot, so that we end up with something that looks like this. Let me bring it up for you. So this is the actual outline of how the components are going to be mounted on the board. I do this because after you've make up the board, it's sometimes hard to see where the little holes, what they're actually for. So, you know, the capacitor, the resistor, another capacitor, the trim pot, and see here now I've drawn up on the heatsink and so on, inductors, so you can actually see where stuff goes. That's usually what I do to make it easier to solder on the components and not to get lost and put them in the wrong place. So now we are ready to start to produce the actual PCB. So we're going to put on the photo-resist and we're going to expose it, develop it, we're going to put the components on, solder them on, and we are going to be testing it. So stand by for that. Okay, so we are ready to put on some photo-resist on this little PCB. I have stuck it down with a little bit of double-sided tape onto this piece of cardboard. Don't worry about what's written on the cardboard. This is just a piece of junk cardboard I had laying around, so I don't get any mess on my desk. We're going to be using a roller. I'll be using this little one here because it's plenty big enough for that PCB. If I have bigger PCBs, I have a bigger roller here that I use, but I won't be using that today. So there we go. Now I have found in practice that you want to put on a fairly thin layer of that. It should still be translucent. You can kind of see the copper shining through. That is most effective for the development. It'll develop quicker, it dries quicker, and so on. And this stuff is pretty hardy after it's been exposed, so you don't actually need a very thick layer. And when you first put it on, you'll probably see some little marks and things on it, as you can see, like that, but I find that is just fine. If you leave it alone, it'll start to spread. Alright, so we have put our negative on top of the PCB with photo-resist on it, and now we are going to put our light over top of it, which is better seen on the other camera. And now we're going to turn it on for 60 seconds, but I will stop the video as soon as I start it. Let's wait for the clock to hit 0. Okay, there we go. Alright, that's it. Now we're going to get our chemicals and to develop the board. Okay, we've got our sodium hydroxide over here. This is always very hard to open. A little bit like that. That's all it needs. Dissolve it. Okay, let's go to the overhead view. Okay, let's plonk it in. You can already see it starting. You can see how quickly that goes. If you don't put too much of that photo-resist on, if you make it really thick, it can take a long time sometimes, but not when you put on the right amount. I think we're there. That's how easy it is. Okay. Now I'm going to rinse it off and we're going to etch it. Okay, I'm just going to put a little bit of nail polish along the edges here. No need to etch that off. Don't really need to do this, but it'll just give the ground plane a little bit more. Copper. Okay, that should do it. Okay, so we've got the ferric chloride over here, and I've got some extra in case I need it. It's in powder form in this container there, but I had some already here that was mixed up, so I've used it about 2 or 3 times. 3 times, I think. This is the 3rd time, and it should still be strong enough, so I haven't added any new. You can kind of see when the copper is gone. The circuit board is actually lets light through it like a phenolic resin, so when it's all finished, I will know because I can just hold it against the light and I can see whether all the copper is gone, which is kind of handy. It's already done in the middle here. I can tell it starts to go darker. See that darker color? Okay, let me have a look now and hold it up against the light. I believe we're there. Maybe just a little bit over here. On the edge, there's a tiny little. Yeah, I think that's it. We're done. Okay, I'm gonna rinse it off now. Okay, so now it's time to hit it with the paint stripper to get the photo-resist off. This container is still pretty full, so I can just kind of dip it in the top here without having to take any of it out. Okay, so now we will just let that soak for maybe 15-20 minutes. This particular paint stripper is modern one without this methylene chloride, and that means it's slower, but supposed to be safer. Okay, so be back when it's done its job. Alright, so we have our little PCB cleaned off now from the photoresist, so we just have the copper. Now we got to go and drill some holes. I drill the smallest holes first, and then I have some extra drills here for the other ones. I have a little guide over here. I printed out with the real hole sizes, so it reminds me which holes are big and which holes are small. And I have 1.2 millimeters, 1 millimeter, 0.75 and 0.6 millimeter drills here, and this is a 0.5 millimeter. They're all different sizes. This resistor here has a very skinny leads on it. These little capacitors are a little bit bigger, but not much. And then we have the diode here, which has thick leads on it. The chip is kind of medium, 0.75 millimeters. These are 0.75 millimeters for the, and so on. So I'm going to be drilling those holes now, and I tend to use this a little tool here that I have, and I will just drill the holes like that. So I just hold it like that, and I will drill the holes. So I'm going to do that. I'll do it off the video because it's a little bit boring to watch. And I'll be back when I've got the holes done, and then we can start to solder it up. Put the components on. Alright, well, we've got the components fitted for fit. See if the holes are big enough. They haven't been soldered in, of course, they're just sitting there loose, but everything seems to fit, so we're in business. So now we're ready to go and solder the components on. Alright, so we're ready to start soldering on the components. The only thing I've put on there so far is a couple of little loops of wire which are going to serve as our test points, but I won't solder those up yet. So I think the first thing I would like to solder on there is the smallest components, because they might be hard to get to once we put the bigger and taller ones on. All right. Okay. Soldering iron. Let's have a look how I go. I may not need to use flux on that since it is all fresh metal, but I'll see. I guess you can see better if I put a little bit of an angle on there so it doesn't look so shiny. And it's a little bit harder for me to see, but because I'm using leaded solder here. Unleaded stuff is hopeless. So what's next? The input capacitor. Oh no, let's do this little trim pot. I think that is good. This is going to be the input capacitor. And this is the negative side, goes over there. Double check. Negative side is here. That's ground. Yep. Very good. Mm. All right. Now I think we are ready to put the chip in there. This is the wire from the test point, and we might as well cover this whole track generously in solder. That way it's got less resistance as well. Alright, I think that's going to do it. Okay. Feedback leg. Okay. There we go. I'm temporarily going to short that out. With a piece of wire. Okay. Just doing this because we want to test it without that last final filter to see what the output looks like before we put the final filter on there. Maybe we don't even need it, who knows. Okay, so I think that's it for the soldering job so far. So now we are ready to start to test it. Okay, so we are ready to start testing the version 2 of the buck regulator. It is connected via these little leads here. This is going to the electronic load. This is the input, and right now I have the oscilloscope probe connected across the diode, and if you look at the circuit, this is where we got the oscilloscope probe across. So we're actually measuring the output from the chip before it gets into the inductor. So let's set that up. So what we're looking at here is the display of the oscilloscope, and we are going to turn on the power supply, and immediately we detect here that we are getting 141.8 kilohertz, which is what the datasheet is saying. It will vary from 140 to 150 odd kilohertz, which is the proper frequency that we are expecting. Remember that the cheap Chinese versions of these chips, including those little power supplies, actually were running at 52 to 54 kilohertz. So already just goes to show you whatever they sell on AliExpress from the Chinese, it's usually junk. They are actually below spec components, or they are fake and they don't even work properly. So this one here that we're looking at is an on semiconductor brand name chip 2596. So already that is a good sign. Now what we want to do is to set this thing up to actually look for the output ripple, and this oscilloscope has some features for that. And then you go to Analyze, and then you go to Power Analyzer, and I have already set it to ripple, which is what we want, and it actually gives you a hint on how to hook it up to a switch mode power supply, which is how we're going to be hooking it up. And you can turn the display on. Let's put it at the bottom here. Okay, coupling for channel 1 should be AC. Bandwidth limit should be set to 20 megahertz. We're going to be using 1x attenuation because this is a power supply and it will have plenty of power to feed the signal. We won't be loading it down at 1 megahertz. Okay, now we want to set acquisition to peak. So that should be the setup. Now let's connect it to the input. In order to get an accurate reading, we will have to put on the little springy thingy. Okay, so we've got it connected via that little, as I said, that springy thingy, whatever it's called, to ground, and this is the output. And we are still seeing quite a bit of ripple there. In fact, 52 millivolts, which is more than what we would like. So I think at this point I'm going to solder on the extra inductor and capacitor that we had planned, and then we will see what we end up with. Right now we're setting that we got it set to 5 volts, and we are drawing. Well, let's play with that for a little bit. We're drawing a quarter of an amp. Let's increase that. Now it is drawing 1.25 amps roughly. And now the ripple has gone to 100 odd millivolts. And so far so good. The actual chip here barely feels lukewarm, so that's a good sign that we can draw at least a couple of amps. So let's actually set that to 1 amp for testing. Okay, so I have mounted this extra capacitor here and this little inductor. So now let's have a look what we get on the output. So let us reset the statistics. And let us now go and turn on the power supply and the electronic load. It certainly looks, those big spikes are gone. Let me adjust the trigger here. We got 20. Let's reset it again. 2 millivolts. Average 22.7 millivolts. Now let's have a look. This is at 1 amp at 5 volts. Let's go and increase the voltage. Okay, that's close enough to 12 volts. Now connect up the probe again. Let's reset the statistics. So the ripple is not actually increasing with the voltage. It's actually about the same. Actually a tiny bit less, maybe 2.44. Now what happens if I increase the current? This is at 2 amps. It's a little bit higher, but not all that much. I think that's not bad at all. What happens when you are at like half an amp? Okay, so now let's test one of those cheap Chinese things and see what their ripple is like. Well, we have connected up one of those cheap Chinese little buck regulators. This is it here. And there are some surprises there. For a start, the regulation is not all that great, is it? If I turn the supply off, it's 5.3 volts nearly. I turn it on, it drops right down to 5.996. I'm not sure if that's within spec. It's at 4% on the data sheet, isn't it? Anyway, but look at the noise on the output. It's like a nasty triangle wave with lots of high frequency components on it, and definitely much worse than the ones we've made. The 134 compared to 24 millivolts. So I guess that shows that those capacitors on there don't have a very good ESR value, and they're not filtering it out very well. So that actually makes us feel pretty good, because the ones we've made is way better than that. And it has a little bit of ripple, but the ripple is kind of like a little sine wave. It doesn't have any high frequency components on it like this. There is another surprise though. This particular little board, I removed the chip that was on it, and I put another chip on there that actually I got from another PCB. I salvaged from another PCB, and I put it on there, and this one does seem to have a higher frequency. According to the little frequency counter there, it says 160 or 170 kilohertz, but I don't really know how accurate that is, on account that it might be measuring something, you know, some high frequency component that's on there that we can't see very well. In any case, our ripple is way worse on that cheap little Chinese thing, so let's go back to ours. Okay, so that was interesting. What we have learned is that these Chinese little buck regulator boards are really junk. They don't have proper output filtering, probably due to the fact that the capacitors that they are using are not low ESR components. So what we're going to actually do, just for fun, but not in this video, but in a future video, I bought these LM2596 deep 2-pack versions. Also, of course, I got them also from AliExpress, so I'm not expecting the best, but we're going to place one of those on this little board where I've cleared all the components off, and we are going to, it has through hole holes for the capacitors as well. We're going to be soldering on proper capacitors, and we're going to make sure that this diode gets upgraded, and I will use the same inductor that they were using. It should be okay. It's not as high in inductors as what we are using on our board, but nevertheless it's 470 microhenries. It should be okay. So we're going to try that out, see if we can actually improve on this. Is it just lousy components they're using, or is it something else? It'll be an interesting little experiment. Okay, so let me set up for the next section. Okay, so I have set up our little board that we have built and designed again over here, and I am putting the probe now again around the Schottky diode over here. So what we're looking at is this. So what we have connected our probe around is this Schottky diode here, and we are expecting to see something that looks a bit like this, except it won't be as nice looking, of course. Some pulse width modulated output. That is what, see, diode voltage, that's what we're going to be looking at. And also remember when we tested that crummy little Chinese buck regulator board, remember what we got out? A triangle wave like that of 150 or odd millivolts or something. So that again, that shows you that the output circuit there is not filtering this out, because this is the inductor current, and that the voltage we were seeing was reflecting this triangle wave. So what we have is this is the diode here, so we are connected over here around this diode. So let's have a look what we will see. Okay, so this is the output waveform when we're not drawing any current from the buck regulator. We've got it set to about 12 volts, but of course when it is when it has no load on it at all, it will go a little bit over 12 volts. So let's start to put some current on. Let's try 100 milliamps first, just for the heck of it. So this is the waveform when you're drawing only a very little current. And the duty cycle is like 27–30%. Frequency 142, 143. Okay. Let's now at 200 milliamps it's starting to look like a proper square wave. 300, no change. Interesting. Wonder why there's no change. This is over 2 amps. I would have expected some change in output waveform. Is something not working here? Whatever, it's two and a half amps. To 12.041 amp. At 2.5 amp, we're getting 11.782 volts. Now, actually, you know what I'm going to do? I'm going to hook up the digital voltmeter, because I'm using rather wimpy wires to connect this to the load, and the load voltage probably is not reflecting what the real voltage is. So hold on for a sec. Okay, you should be able to see the voltage. Alright, you should be able to see the voltage now at the top right hand corner. You got 12.202. That'll be more accurate than what the electronic load is saying, because this voltmeter is connected to the actual output directly before it goes to the load. So let's have a look now. Yeah, you see I'm at 2.5 amps now, and we still got 12.135 volts. So we're actually dropping some voltage across those little wimpy wires that go into the load there. They're not very thick. So it is actually regulating quite well. Alright, so let's have a look what happens when we lower the voltage to 5 volts. Because we're actually inputting 20 volts and 12 volts is closer to the input voltage. So let's have a look. See if that makes a difference. Yeah, that does make a difference. See? Looks like that square wave that it outputs is actually relative to voltage more than current. Interesting. Okay. It's really touchy to adjust even with the multi-turn part there. Let's leave it at that. 5.05, 5.06, close enough. Okay, so now, oops, I knocked the camera. So let's increase the current. Well, let's go down first and have a look if it looks the same. So this is what basically with no load, very little load. This is with 100 milliamps. Looks like at 200 milliamps it stabilizes. And indeed that square wave does not change. It is relative to the voltage that you select. So the higher the voltage, the longer the okay, well, that was an interesting experiment. I thought the square wave would change with duty cycle according to the current that it was outputting, but it seems to be only changing when you change the voltage. Probably means that even at a couple of 2.5 amps, it is well within the capability of the circuit that we've built here. Anyway, so it doesn't have to modulate the waveform much, if anything. So that is, I guess that finalizes our test. This is at 1 amp. We got, let's check the output voltage when I reduce the current. 5.08, and at half an amp it's 5.06. It's supposed to allow to vary by up to 4%, it said on the datasheet. 1 amp, actually that's 1 amp, 5.04. 2.6 amps, 5.01. It's supposed to be able to do up to 3 amps, but I'm not going to let it go that high because I really designed the circuit to be good for up to 2.5 amps. Yeah, it's regulating quite well. It goes from 5.04 to 5.02, so that should be within the 4% range. Better than what it is allowed to be. Alright, so looks like we can build a successful buck regulator. So the next job is going to be, where's the other, is going to be trying to build the negative 12 volt version. So this is a preliminary circuit. I have to put a bit more work in that to now the things that I've learned from building that standard buck regulator. But in any case, this one is going to have 12 volts going in. It's going to have pretty much this circuit, but I might have to I will change some of the value of these components. And there's also going to be a little linear regulator to provide plus 5 volts. This is for an upcoming project that I'm thinking about, which I won't quite reveal yet until I make a decision on when to do it. So that's going to be the next project. Oh, well, not the next project, but that's an upcoming project. Okay, so that's all we've got for now. I'm pleased with how this little buck regulator worked. So I've learned a lot from that. I think if you're going to use this thing for over 2 amps, you are going to need a bigger heatsink than what I've got on here. But there is enough room on the board. I can use a bigger heatsink on there. That's fine. And we'll see where we go from there. Don't forget to like, subscribe, and all that sort of stuff. As I said before, I need quite a few more subscribers before YouTube will recognize me, and before I might get suppliers sending me stuff to evaluate and stuff like that, which would be kind of fun because I got limited funds and I don't want to keep buying my own stuff to test. Anyway, I'll see you guys later.